All right, let's get going. Hello everyone, thank you so much for tuning in. Today I'm going to talk about a workshop paper that I'm working on. It's about deploying a unified abstraction layer to facilitate attention-based deployments on edge devices, namely iPhone devices. Currently speaking, I'm working on extending this work to Android devices or other edge devices as well. So before I start, first I want to talk about two main phenomena in deep learning model. One is the training, the other one is inference. So training is the process of creating a model and teaching a model how to make predictions or decisions, usually by understanding a learning pattern inside the data that they have, and then create a result, create a prediction. You can think about it as a classification task, and then from there you can find out how much your prediction is different from the actual label in the validation set, and then based on that use backpropagation, which is the second pass. Once you do the forward pass, you do a backpropagation phase, and then you use chain rule, get the gradients of the last layer. Based on that, you calculate the partial derivation of each node, and then go back. So forward pass can be treated as a parallel computing. You definitely need like parallel processing, decomposing features. Let's say if you're talking about a vision task. So you're talking about a lot of GPUs to do multiple parallel processing for you. This phase is usually done offline. However, once your model is built, you're actually pushing the inference, the model to be deployed to the unseen data. So the performance is measured with contrast to the first phase, which is training, where the performance is measured based on accuracy and loss. Here, the performance is measured based on latency and throughput. So latency is how long does it take for the model to ponder upon the underlying patterns and give you the results. And throughput is about, in a fixed amount of time, how many predictions can I generate. And this happens in hopefully near real time. And it's on unseen data, it's on test data. And then because of that, you're only doing the forward pass, you're not doing the backward pass, you're not adjusting the weights of each neurons and each layers. Therefore, it can run on less powerful machines or on edge devices. So that being said, I'm going to talk about the overview of my talk today. I already talked about training versus inference. I'm going to talk about deep learning model optimization basics. I'm going to get a little bit into quantization, pruning, distillation. Then I'm going to talk about just-in-time translation, namely tracing and scripting, which is built in for PyTorch. Then I'm going to talk about the current process, the PyTorch to CoreML transition. Again, specifically I'm focused on Apple devices and Apple platforms, so I'm talking about the CoreML transition. I'm going to lay down the gap in the current process, and then start to introduce Hardware Abstraction Layer as a solution. And we're going to see some high-level pseudocode in practice, and then I'm going to briefly talk about the results. All right, so once we build a model, a deep learning model, and we want to deploy that in any targeted hardware, assume that the targeted hardware is an edge device. So what we're trying to do, let's say right now we're talking about the state of the art, which is foundational models. They're too big to serve directly on an edge device during inference time. They're very computation intensive. They're big to put on a device, not to mention they're even demanding more computation to run. So they're big in size by themselves, and they demand more computation. So we need an abstraction representation of a program, which happens using the intermediate representation. I'm going to call that IR, to abstract the computation process of the program and just tell the hardware what needs to happen next. So creating, as you see on the bottom left corner, you have computation graphs. The blue is the forward pass and the green is the backward pass. Obviously in the inference time, you're not looking at the green, you're just looking at the blue. But then what part of that can be deployed parallelly versus completely sequential is what the IR is taking care of, and how to take advantage of the hardware utilities and what the hardware provides for you. For instance, if you're talking about Apple products, you're talking about neural engines that Apple products have. So IR can act as a bridge and converts a model from one framework to another. That gives you the possibility that you don't have to worry about where your code is going to be deployed. So you're actually thinking about cross-platform facilitation, meaning that you just write your code in TensorFlow, Crass, or if you're old school like me, Tiano, like old days, and then you can just transfer it, as I'm going to talk about in a few next slides, transfer it to your targeted hardware. Just tell the hardware what to do and be good with that. But the cons are, once you want to deploy to the hardware, once you create that abstraction, as you know, there is no free lunch theory, meaning that once you want to deploy, you're actually losing part of that accuracy or efficiency during this transformation. Not everything is going to transfer perfectly. And then another thing is, depending on how you split your training and dev set for creating the model and how the test set is actually compliant with that distribution of your test and dev, you're going to have the problem of generality, meaning that how your model generalizes on same data, and a specificity, meaning that how deeply the model understands and have expertise to answer specific questions or a specific part of the images. For instance, if it's an image application. All right, let's get a little bit into quantization, pruning, and distillation as the techniques for deep learning model optimization. So quantization first is, simply put, you're reducing the precision of the numbers used in a model. And by numbers, we're talking about weights of a neural network. So you're going from 32-bit float to 8-bit integer. As you see in the picture, you're decreasing the model size. But then, since you're using less bits to represent the weight, you're actually losing part of that information that you're not using. So again, you have to maintain the accuracy, and that impacts on the accuracy. The second technique is pruning. Pruning can be divided into two different tasks. One is removing neurons. The other one is removing the weights. Here I'm mostly talking about removing the weights, and the reason for that is that you're reducing the model complexity, meaning that you're creating more sparse matrices, and then once you're multiplying sparse matrices, it's actually easier. It takes less energy, less effort, less memory on the edge device, specifically on inference time, and helps you to reduce the latency, for example. And the distillation is actually a training phenomena, but I put it here because it's a deep learning optimization technique. So assume that you have access to the teacher, the main model, that the main model's labels, the prediction that a model creates. And as a student, you just want to cram all that information in a smaller model, meaning that you're not here trying to understand the underlying patterns in the data. You're just trying to memorize everything that the main model, the teacher model, creates, calculate your loss, and just learn to predict those outputs. And that's it. And since it makes the model smaller, the model is more compact, and just distill the model and then deploy that. And as I mentioned, this is a training phenomenon. All right, so I'm going to talk about the conversion pathway. So as I mentioned, there's an IR, there's an interrepresentation that helps you doing that. So you can use PyTorch and then ONNX, and ONNX is an open source format. It actually does all the good things that I talked about, the pruning and distillation and quantization for you, namely quantization and pruning here, and then gives you that interoperability. And once you get the ONNX format, you can actually deploy to any other framework here on CoreML, which is a Apple framework. However, and you can deploy it on iOS and Mac. However, there's another built-in phenomenon created, which is called torch script. And torch script is sort of, you can think about it as a PyTorch interpreter on top of the Python. It runs independently of the Python and enables your deployment into a variety of environments. It gives you that cross-platform facility, and it creates a more optimized and portable format because it deals with the actual PyTorch types instead of the object formats compared to the ONNX. And I'm going to get deeper into what do I mean by that. So here I'm going to talk about tracing and scripting. We're getting into starting to get our hands dirty with Python. So in Python, once you write the code, Python is a popular language regarding if you're using a Keras, Theano, or TensorFlow, you're talking about Python. So once you write the code in Python, using this concept called just-in-time tracing, and it helps you when you do model.eval to serialize and optimize the computation nodes required for deployment on the hardware. And what happens, and what do I mean by that, is that it actually, the interpreter of Python just does its work. When it gets to the point of deploying something regarding your deep learning model to the hardware, it actually turns that on, and in time it translates it based on what is available at that specific point of time on your hardware. And this means that your script model can actually turn into one or more than one part of the pipeline of the application in the targeted core ML model. And there are two phenomena here, tracing and scripting, that I'm going to talk more in detail about those. So tracing means that you're having a batch example, and then you want to actually, and then you have only one control flow of the information of your data all the way to get to the decision making and inference inference phase. So you capture the operation performed by a model, and then running an example on that, you find out what needs to happen for a computation graph that is static. And then since you don't have any control flow or any iteration or anything like that, you basically get what it needs to happen on that core ML for Torch script model. You just create that Torch script model, and that's it. This gives you actually very robust, lightweight model, but again, as I mentioned, it's just for a static computation, sorry. All right, and now I'm going to talk about scripting. So what happens in the scripting is that once you have a control flow, let's say iteration or decision making, you have to wrap the model in Python-like annotations, and I'm going to talk about that a little bit in the next slide. But you have to capture the control flow, meaning that you have to capture the full model instead of just blindly understanding what happens and in the hardware time. And then because of that, you need to deal with the object types, because you're talking about what happens in the compile time, and for that you have to actually understand the object types, what the compiler is dealing with at the time and what is available on the hardware side. So trace produces simple representation. A script needs the type information and the object type, and you need to completely and directly compile the whole model. The best practice is to create like a hybrid strategy, meaning that where you don't have the control flow, you just do the tracing, and where you have the control flow and you need to get the full model, you just do scripting. So combine those two parts together. Now, as I mentioned, I'm going to show you what does it mean to wrap something in Python-like model. So as you see, like here, I have a class of neural network that it actually gets from Torch, endowed module. Forward is very simple. It's a convolutional ReLU, then average Boolean dropout linear. This is a very straightforward, very simple child stuff. I mean, like a very vanilla stuff of vision application, and then you just do the scripting, and the result is a scripted model. But again, this is a heavyweight, and you want to stay away from that as much as you can. So now I'm going to talk about the problem. What happens if you want to trace versus a script, and then what are we talking about? So here, as you see, I created a model, like the model that I showed in code, and now I'm just saying like trace the model as just the model that I showed you in the previous example. And then you see like I get a trace warning, although you can maybe ignore that, but in deployment you will see that that's going to create problems. So the model slices tensors based on the size of another tensor. And what it means is that it's a bare Python value, not PyTorch. If you remember, I talked about you're doing this whole torch scripting to create a PyTorch value, not Python value. And once it happens, you cannot trace, let's say, math operations based on bare Python values on the inference time in your targeted hardware. Therefore, you cannot generalize to unseen data. Let's just show a very quick example in code, and I tell you what do I mean. So when I'm tracing Python values, the first line, I'm slicing basically a tensor based on the size of another tensor. I'm cutting the rows, cutting the columns of a tensor based on the rows of one tensor. And this operation is doable in tracing. Doesn't matter. This is not subject to interpretation. That's what I mean. And for padding, you're basically looking at remainder of, let's say, this tensor number of rows to the other tensor of rows, and this operation is also doable using tracing. However, when we're doing math square root, when you're doing a square root to create W in the third line, this operation is subject to interpretation. What do I mean by that? Is that once you're doing the square root function, what happens is that it doesn't know, am I talking about PyTorch value or Python value? And that actually creates a problem in the next line when we're calculating the NDNNS based on the size. And here the size, if you're talking about 8-bit versus 32-bit Python value versus PyTorch value, you get different results. Therefore, the value of B in the next line, the fifth line, is also dependent on how did you interpret the third line. So then again, as I mentioned, the model slices tensor based on the size of another tensor. And then if it's bare Python value, then you're going to have trouble tracing math operations like here. So the idea of how is that what if I actually create a key value abstract cache, and then I keep that cache somewhere, make sure it's not getting stale for all the transformer-based decoder type on the decoder side. And since I'm streaming data, chances are, let's say I'm looking at frames of image, chances are I'm not moving my camera too much, so most part of what I calculated for my cache in the first frame is reusable in the second frame, so on and so forth. And this cache is updated whenever everything changes drastically. Then I calculate the key and value and put it there. If not, then I just reuse what I have in my cache. And this mechanism is partially available, mainly available because we're talking about attention-based model. In attention-based models, we have keys and values and queries. So if you're actually using key and value as the cache, the query can be, you can look at the query as the streaming data that is coming. It could be your text, it could be your voice, it could be your video frames that are coming to you. And it ensures consistent interpretation of types and enhances reusability between different attention models. This way, if you're calculating everything and putting in cache, then you don't have to worry about if this is script, if this is a math operation or not. You just calculate once, however it is, you just put it there, and then you can reuse it if the value is needed again. So this means that this phenomena actually comes at the end before in the IR, in the intermediate representation, and this creates an abstraction on top of that abstraction of the computation. So you're generating a abstraction of a compiled object, which is hardware agnostic. By hardware agnostic, I mean you can reuse that across that same computer architecture, let's say namely ARM here, because we're talking about, again, Apple devices. And these objects, this cache mechanism can be used and reused across different attention based on the decoder side again only, of enhancing efficiency and reducing the need for model specific operations. So what does it mean for us? So you can actually optimize the memory layout for attention matrices. You can parallelize this heads calculation because you have cache right now. You can actually calculate them in parallel. You can optimize the sequence packing. You can take care of recurrent layers of caching mechanism, because chances are you might not need to memorize very long of the history versus everything that is in short term. And you can just keep everything that is in short term in your cache. And I'm going to talk about like very few examples here. So for instance, in facial recognition, what you do is that you can actually keep the accuracy the same while you're maintaining contextual information from previous frames to the future frames. When you're checking the faces, your angle might not change. The faces from this frame to the next frame in terms of streaming might not change that much. So you can actually use the cache for that, for facial recognition video streams. You can actually cache the object detection in video stream, and then you can actually remember that information across different objects for faster detection for processing sequential frames. And for image segmentation, same idea. You can actually cache regions from one frame to another frame. Chances are it's not changing drastically. And this is particularly useful in scenarios that the scene changes are incremental. And I'm going to show you a very quick example, high-level example of the KV caching, key value caching. So this is a very abstract layer of thousands of lines of code being written here. So I'm talking about cached multi-head attention. You can think about it like, simply put, I have a cache mechanism being put in my multi-head attention container or multi-head attention. And then in forward pass, once I split the inputs for each head, then I calculate the cache. As if you remember, I talked about parallelizing of different head. For each head, you can have key value pairs. You check if the key value pair is already calculated and put in your cache. And you can actually have also a stale mechanism for your cache, for eviction of the cache. So if something is not being accessed in cache, you have to evict that from the cache. Or if something is in the cache, but your cache is full and you need to bring some new value in, then you have to evict the value that is least recently used, L or U, and then update the cache. And you update the cache for new value pairs based on different methodologies that you can use across the board. And you compute the attention for each head, for instance, in this case, and then you concatenate all the caches, then concatenate all the heads, I apologize, and then pass through the final layer and output the computation code, which in this case is like the attention output. All right, so here, table 4 of my paper, I put all of these performance matrices for various tasks on iPhone using this abstraction layer. As I explained and mentioned about facial recognition, I used state-of-the-art models that is used for video streaming, object detection, image segmentation, speech recognition, language translation. And then I put latency, memory usage, model size, and the accuracy. As you see, the accuracy is actually very, very reliable based on the size of the model and the memory footprint of the model that is used. And the latency is very reasonable. So here I'm talking about the latencies that is actually very useful in real scenarios in terms of like 10 milliseconds, 30 milliseconds, in terms of that is actually usable. Hopefully it gets you interested to reading the paper and I get good questions at the end. But some future endeavors that I want to talk about is that I'm tapping into the energy efficiency optimizations. We know that attention-based models are very computation heavy and demanding. That drains the battery of these devices that are running on lithium-ion batteries mostly. So that is something that I'm working on in the near future. And then another interesting idea is that load balancing across multiple devices. You can have different devices, and then each device can calculate part of the cache depending on the angle. Let's say you're looking at, like a vision model. And then since the operation of fetching cache is way faster in a network than computing the attention heads, so it's easier, it's faster to just pass the calculated cache instead of recomputing the same actual values from scratch. And that gets us to auto-tuning these models, the models that can actually create a cache and this cache gets automatically updated. So these models are working with a bigger model on the back end, and they can actually, by just using the cache, they can make smart decisions on the go on the inference time while we're not deployed the whole model on them. All right. Thank you so much for listening to me, and I hope you enjoyed my talk.